So good afternoon,
Yeah.
everyone. Welcome to the second lecture of this mini school on the topic of machine learning, from physics to machine learning and back. Yeah, and the second speaker in the series is Dr. Pallab Basu. Pallab is, sorry if I remember correctly, please correct me, is a senior lecturer at WITS University. And he's a theoretical physicist, and he will speak today. So his work is on string theory and quantum field theory, in particular ADS and CFT issues. Yeah, and today he will speak about the relationship between machine learning, statistical mechanics, and in particular focusing on spin models. Yeah. Pallab, did you manage to to sort out?
Yes,
Okay.
yes.
You're welcome to share. You're welcome
yes.
to share your screen. And maybe while you do so, I remind the participants, please make use of the Q&A facility to ask questions. And at the end of the talk, if you want to ask a question in person, just raise your virtual hand, and I will give you the right to speak. Yeah. So Pallab, thank you very much for being with us today. The floor is all, the virtual floor is all yours. Yeah.
Yes, sure. So I have to do the screen sharing. Sorry, I'm not super familiar with.
It's the green button, and then you can choose the window in which your PowerPoint or PDF or whatever technology uses, and select it.
Yeah. Share screen. Yes, I get it. So yes, yeah. Thank you. Share. Okay, is that working?
Yeah. Perfect. Now we see your
machine learning of criticality, a spin system approach. So should I start now?
If you want to make it perfect, you could click the full screen view if your PDF allows, so that we don't.
There is some, it seems that was the problem. There is some problem with the PDF, it seems like.
Leave it like
I'm not
this,
getting into
don't
that.
touch it. That's fine. Don't touch it. Let's leave it like that.
Okay.
Please, over to you.
Sorry for the delay. So this is machine learning of criticality, a spin system approach. So what are we going to talk about today is that we'll just discuss a little bit about machine learning, and we will discuss few applications of machine learning in understanding the nature of Ising criticality, and especially I will concentrate on my paper on machine learning, the recent work we have put into. So I will concentrate on that. Okay. So the first, before getting into anything specific, let me just introduce you to what is machine learning. So before getting into Ising model, spin system, or anything of that sort, so what is machine learning is that at the end of the day, any learning is a generalized fitting. Fitting means that if you have few points in the screen, say, so if you have few points in the screen, can you see my points? Yeah, so X and Y axis.
Sorry, I was on mute. We can see it. We can see it. Yeah.
You can see it. Okay, good. Thank you. So the thing is that, so these points, say, I tell you to fit a curve through them. So this is just a one-dimensional fitting, one variable, y and x, some data points are given, and you are trying to fit it. Then once, if I ask, what is the value here, you would get, so that, what is the value of y at this point? From this card, you can find out this is the value of y. So this fitting can also be used as a prediction. Good. So okay. So machine learning, as we have just discussed, is nothing but a generalized fitting, where we actually have a huge amount of data set, and within that data set, and just rather than few points, we have a huge amount of data set, and we are doing a fitting on those kind of data sets. And the data sets could be very complicated. For example, faces of dogs and cats, or dog versus cat. And through this fitting, you want to tell which face is which, and those kind of things. Generally, we do not view machine learning, but it really is. Now, what is the difference then between simple parametric fitting versus machine learning? Both need training, and then there is there is a parameter optimization by minimizing a chosen loss function. Good. Now, however, in learning, we should there is one thing is that what happens is that, as I've just discussed, that say we have two axes, X and Y, and if there are few points like this, we can draw a straight line through this point. This is called a good fitting. However, you can overfit those and fit a curve which goes through many points. However, this kind of fitting, which actually looks very exact, actually is not a good fitting, because these curves are a huge number of parameters. So in general fitting, what happens is the parameter, your fitting actually gets worse. What does it mean by the fitting get worse? Fitting get worse is that it looks like this fitting, this curve goes through all the points that is given, that is all the training point, but when you test it, result could be very bad. For example, the straight line possibly gives an okay prediction for an X. Here, what happens is that your prediction becomes very large or very small, or something way off what it actually is maybe in reality. So that is a problem. Sorry. Yeah, why the... However, sorry, this chat was thing, I think.
Sorry, Pallab, what is the...
That's fine. That's fine. I just opened the chat window. No. Okay. Now, the thing is that in machine learning, on the other hand, what happens is that as you increase the number of parameters, as you increase the size of the net that is doing the fitting, strangely, the fitting gets better. For example, what one expects that, say, if I plot the loss function, that is, what is the total loss of a system, loss function on the test data, not the training data set, but on the test data set. That is, you train the model as much as you like with many parameters. How this loss function varies on the test data varies with number of parameters, or n, which is number of parameters. What happens that as you increase the number of parameter, obviously the function gets better, so your loss decrease. However, if you increase too much, then this loss will revert and go up. That is true for ordinary fitting. However, in machine learning, what we have seen is that we are mostly trapped in this region. And if we increase the, especially numbers of parameters in terms of number of layers, we'll describe what it means by layers, etc. Actually, the machine, this fitting goes better, it does become worse. It only becomes better and better. Okay, that is a difference between ordinary machine learning, as we have seen, and people are trying to explain those things, or whether that is true for any situation, those questions seems to be hard. People are working on that, mathematicians, etc. But this is what we see. Okay, now as you can AI generated things that you have possibly seen in internet, etc. All are generated this kind of network, which is called machine learning. We'll describe those networks in the next uh, what is ANN, etc. You have seen these faces are not real faces. They are generated by machines. And now we also have Chat GPT, which I'm not talking about here, which speaks like a human. And apparently some people say that it is intelligent and has its own mind, which may or may not be true, even we don't know, of course. And this is a picture of some kind, this Los Angeles or San Francisco, some bridge in a Van Gogh style. So all these things that the machine somehow learned what is the Van Gogh style and implemented that style on some other picture, etc., and can generate these spaces all through this kind of hugely parametric fitting. So what is so great about this kind of machine learning? It has been seen that at least what is known now is that the machine networks, the fitting system we use are called, the most generic ones are called ANN. So this is ANN stands for artificial neural network. Now, what again, you can anyway do a multi-parameter fitting. So what is so great about it? Generally, multi-parameter fittings are not a good idea because if you have few thousand parameters, to find a proper gradient in these spaces, you have to calculate all those partial derivatives, and that's a huge job. And generally, you can't do it. And even if you can do it, it's very messy. This fitting has a lot of local minima, etc. But that doesn't give you nice results. But what has been realized, just experimentally, whether there is a theory for it or not yet, the thing is that if you take something like what is called a neural network, which is somehow inspired by biological neural networks in our brain, although I must point out whether those two things are exactly same or not, again, is a different topic and question. However, people do say that they are inspired, not may or may not be the exact copy. So what happens in this kind of network is that this kind of system, this is basically a graphical representation of a network, or it is actually the function. So what function is that which we are trying to fit and optimize, etc. So these three are the input of this function, say function X, Y, Z, etc. Now, in each layer, what's happening is that you take those inputs. So and then in each of this block are creating various kind of linear combination and sending them to the next node. And inside this node, there is a function sitting. So what does it mean is that, say, you put something x1, x2, x3, then some linear combination of x1 and x2, say, wij, xj, is the weight of this link. So this link, if you put x1 here, maybe w1 to x1 is sent to this node, some other combination is sent to this node, and we have a summation of all those things coming from all those nodes in the previous layer. And inside each layer, and there may be some kind of thing called bias or something, that each node, the linear combination. So when it sends here, there is a bias associated with that node, that it's not linear combination, but it adds some constant with that. And each node, what they do then is that they put a nonlinear function on that signal. So you put x1 here, x2 here, x3 here. So W1, say this node is say J. So W1J, x1, W2J, x2, W3J, x3 comes here. Then you take this linear combination, add a necessary bias, Bj or something parameterized by this node, index of this node, and then this node put the whole thing in a nonlinear function. Often these nonlinear functions are called activator functions. What is an activator function? And before going into activator function is that then this process continue through each layer. Then this node will say different function. So what are the parameters? So at the end, you get a linear combination of function, then again a linear combination, again a function, linear combination, this kind of nested thing, which is not very difficult to write, but it looks complicated when written down. So just a nested thing. And then at the end, you take a final linear combination and may put a final function, and that's how you get one or in sometimes many outputs of the neural network. So this is the whole thing is just approximating or creating a function. And what are these function parameters of this function? Parameters are these Wijs and Bis. These are called weights and biases of the neural network. Those things, those are the parameters we are going to optimize at the end. And what is this function? These functions are generally called, which is sitting inside each neural network, each node, are generally called activator functions. Means that they can come in various shape. One popular one previously was just a tan hyperbolic like thing. Tan hyperbolic means that it is 0. If the input is negative, it becomes 1. It's more like sigmoid, means 1 plus tan hyperbolic by 2. And it becomes 1 if the input is 1 or more. It tends to 1. Nowadays, people use another kind of activation function, which is 0 if the input is negative, and become a linear function if the input is positive. That is called ReLU. That is something people use a lot these days. But in general, it is generally is this kind of function. It suppresses one side of the input and enhances other side of the input. So these are more like something, a light bulb, which flares up when you put correct linear combination, feed them correct linear combination. So at the end, through all this complex function and all those things and all those light bulbs, you may think that are lighting on, they trying to capture various complicated functional form constructed out of these inputs and try to capture complicated features like what is meant by eye in a human face. How do it could even be a in chat GPT like scenario, it could be some kind of text, and the question is that what comes if I say I am a boy, or you are a boy, so what comes after I, what comes after you? It is kind of generating those kind of correct inputs. Okay, so that's how this a generic functional approximator works. Now, more advanced neural networks generally do not use this setup. There are other advanced forms which are called CNNs, in the case of ChatGPT, etc., called transformer neural network. But basic idea is this nested structure. What may happen is that you may put some specific function here. You may not use all the links. It may be that some links are only connected with this kind of, some links from the CNN, etc. Some links, so various links, etc. may do various other things. It may not be a generic neural network, but some subset of this generic neural network, which is intelligently chosen for some specific job. So all the neural networks has this generic form, but specific ones are, you may think that they're a subset of this general structure, roughly. Now, why this system, what's great about it? Because you see that this system has a huge number of parameters. All links I have said that correspond, there's a weight corresponding to all those links, and then there are biases. Biases are few, but the links are too many. So this setup is almost impossible to optimize. It seems that there is a way called backpropagation because of this nested structure. You do not really have to calculate all those partial derivative with respect to weights, or means if you want to optimize some kind of loss function or some function, you don't have to calculate all the derivatives respect to all the links. You can calculate that somehow some suitably chosen derivatives that are known, and you can reconstruct the derivatives of the links by some linear combination. This method is called backpropagation, and this backpropagation makes these models very easy to train. Not so easy, but at least tractable. So you only, if you have 1, 2, 3, 4, 5, 6, 7, or 10 nodes, you just have to do approximately 10 derivatives, and you can construct the derivatives in each node, each of the link, which are much more numerous. And that's way you can easily do a gradient descent kind of fitting in this model. Okay. Okay. Now, before getting into that, so what will be our goal is that, okay, so we have this generic neural network, etc. So what? So what is that we want to do certain experiments which has already been done by people, and is that, as I've said, that this neural network can classify things. For example, classification is also a fitting. For example, here you can see that some faces would generally people will identify as female faces and some as male faces. So basically you can say that these some faces will put a value of 1, some faces will put a value of 0, and that's called classification. So classification is also a generic fitting. Fitting is for a generic function. Classification means that you fit a 1-0 function over a data set. For some value it is 0, some value it is 1, and then a new value comes. You have to whether this for this value is it male, female, cat, dog, or whatever it is 1 or 0. So we are not even using the full capacity of neural network. We're just using it as a most simplified fitter, which is called classifiers. Okay, so what is has to do with Ising model, etc., etc. Okay, so let me just quickly introduce you to two-dimensional Ising model. So if you take a lattice in 2 dimensions, there are up spins and then there are down spins. So, okay, so sorry, if you let me introduce what is meant by a spin model. Sorry, some of you may not be familiar with that. So basically, spin models are a theoretical approximation of magnets. So how magnets function is that you may think that there are several atoms sitting inside a lattice of a material, for example, iron or something. In a very simplistic picture, each atom is a small magnet which can point up and which may point down. Now, what happens is that when 2 atoms are pointed in the same direction, that means that you put direction, apparently in some situation, this combination may have less energy than a combination where the neighboring atom has different direction. So if one is up and the other is down, that has more energy than both up or both down. So there is an energy gap here. So this is energetically more favorable. This is less favorable. Spin model. So what is the Ising model is that you take a lattice, it could be in one dimension and often in two dimension. We won't get into the one-dimensional thing. We have also worked on one-dimensional thing, but two-dimensional, the physics is more interesting, and I'll tell you in what way. So each point of those lattice harbors one spin, and this spin can point upward, and this spin can point downward. Now, if these spins are completely randomly distributed, there is a half-half probability that they will be up or down. However, in Ising model, it's not random in a way that there is a energy function, as is common in statistical mechanics often, which determines that whether an configuration is probable or not. So with each configuration, we have an associated energy. In the case of the Ising model,
Hello, it looks like we lost the speaker.
Yes, correct. I'm still here, Francesco. It looks like
no, sorry, I was not sure whether my network went down or the speakers went down.
Yeah, it
Let's
looks
wait
like
a minute.
that side, yeah.
Yeah, let's wait.
Just wait a moment.
Participants, sorry for this, but you know, we live in times of heavy load shedding, and maybe let's wait that. Let's hope that the generator kicks in at WITS if it is due to load shedding. Yeah, I will check in the meantime if I have an email from the speaker in case he sent us one. No, not yet, but let's wait a minute. I'm sure he will be back in a second. Please just don't leave. Stay with us. Let's give the speaker the opportunity to join again. Yeah.
In the meantime, I'm just saying hi to some of the people we haven't seen in a long
Please.
time.
We should say hi to everyone. Yeah,
yeah, exactly. No, absolutely. Analaba, Roy. Oh, I just see Analaba. Are you there? That's one of our previous researchers.
yeah,
So that's
yeah.
nice.
Yeah, no, there are lots of people. Yeah, yeah, excellent. No, thank you very much for your patience, guys. Let's hope that. Yeah, no, I see Asif says he thought there's load shedding only in Pakistan. Unfortunately, not. You are in good company, Asif. Okay, Pallab is back. Pallab, we
so the quality
you...
of internet has gone down, unfortunately.
I know. That's because of the heavy load shedding the last couple of days. But we are all aware of it, so we just kept tight and waited for you. So please, Pallab, without further ado, just...
Okay. So if two spins are up, then it is 1 and 1 minus 1 is or minus j, or it comes with a negative sign. So similar, it is energetically favorable to have the spins in the same direction, and energetically unfavorable to have spins in the different direction. And as you know that the spin system can be approximated again by 0, 1, so you get a picture like that. Black in some place, black is down, white is up, and you calculate the total energy, sum of all these energies in the system, and you say the probability of having this thing is minus beta into that energy. And beta is a parameter which sometimes called inverse temperature. Basically, the idea is that as you change this parameter, this most probable configurations would change. For example, if beta is very low, that means that the configurations which are low energy will dominate over configurations which are high energy, because their energy gap, because beta low means that there will be huge difference between high energy and low energy configuration. So sorry, no, beta is not low, beta is high. When the low temperature means beta is high, then what happens is that low energy configuration will dominate over high energy configuration, and low energy and lowest energy configuration is the configuration where all the spins are pointing towards the same direction, and that combination will dominate. However, if you change the value of beta, what happens is that other combinations may start playing a role. And whereas these combinations with all spin upwards has low energy, is also unique. There is just one such combination, whereas random configuration is more numerous. So if you change the value of beta, what happens is that there is what we know as phase transition. So what happens is that as we vary the value of beta, we may come from a phase where everything is pointing towards the section to something which is completely random, and various things are pointing towards various other directions. And in Ising model, there is a critical temperature. If we use this notation, it is about beta is equal to 2.245 or something. At that value of beta, this nice combinations change into random combination. And this is a very classic result in physics. These two kind of combination are, there is a second order phase transition between these two kinds of combinations. But I will talk more about the second order phase transition, but let me get into machine learning of those things. Okay. So what is meant by second order phase transition? We'll come and explain to you what is meant. So basically what it means is that you, as I was discussing, when you start, all the spins are set down. So down, I represent as black. So at value, lower, higher value of beta, everything is down. And as we change the value of beta, you can see this cluster. And at around sometimes around this point, this cluster become of infinite length. This destroys all the order in the system. And if you look at any quantity here, for example, like the popular is energy. So this is correlation length. So basically the size of the cluster, correlation length jumps up and becomes almost infinite. Finite lattice, finite, and then correlation length is small, because here what happens is that all those dots are small. Here correlation lengths become infinite, so these white blobs become very big, and when you heat it up, then everything is random, and there is no white blobs has the same frequency of the black blobs, but they roughly have the same size. So in that case, both are small, so the correlation length decreases again. If you look at something called magnetization, magnetization means emission So what we see at 0.25, there is a sudden jump. This is the green curve of where the magnetization was 1 before it suddenly becomes 0. It looks like a smooth curve, but if you have a finite system, we are taking a finite system of 40 cross 40 size. But if it were a finite system, these jumps exactly, these jumps would look more like this. So these curves would look more like this. In one side, magnetization, that is total summation of spin, is exactly 0, and at critical temperature, it suddenly jumps up and becomes 1, etc. So this is again a point of second order. This kind of thing is called a point of second order phase transition. Good. So this is can calculate other thing like specific heat, etc., and we'll see infinity, but specific heat and correlation length, they both with there is something on critical indices, they are both correlated, both becomes infinite, etc. at this point. And this is the most famous example of second order phase transition. Now, as you can see that as you have this all these different pictures, etc., so you may, in principle, try to teach machines that how to distinguish between these pictures. And many people, many groups around the world, some in Europe, some in Canada, has done this work, etc. And they have, what they have done, basically, that in the simplest form, they've shown machine these pictures, and when a new picture is shown, machine is like with the base, the cat, dog, male, those, the machine has to correctly that which phase the picture belongs to. And it seems that the machine can do that. And there are several papers, very highly cited papers, which people have done. Has also been done for several different models related to Ising model, etc. Now, so there are previous works, so distinguishing phases, order versus disorder, train a model with, so what we do is that we train this model, we generate those phases through a method called Monte Carlo, and we train the neural network through Monte Carlo data and present the neural network with a new configuration and ask whether this configuration and ask for classification of these configurations. And many results, cool results are derived by the group or uTorrento group, but there are many other groups who also work on the same thing. Now, unfortunately, although this looks that machine can distinguish between phases, etc., this is a much simpler problem than learning about other kind of pictures, more complicated drawings, etc. And why is that? Why is that? Is basically machine learning Ising model has a simple magnetization versus temperature graph. So magnetization is 1 at some phase, becomes 0 in some other phase. So machine can just learn magnetization. And what is magnetization? Is just the summation of spin. And I was saying that goal of machine learning is actually to concentrate on very complicated function. You don't need any kind of complication. You can just take the summation of the spins, and there is no wonder that's what machine learned easily. So now our goal is a little different here. What we want to do is that if you look at this picture, you see that this picture, this is called critical region transition. Now, what we want to do in this work is that we ask two questions related to machine learning. So, whether we can teach the machine the concept of criticality, really, the second order phase transition. And for that, what we want to do First is that we don't want the machine to learn a simple 0, 1, that whether its magnetization is 0, magnetization 1 kind of dynamics easily. So our learning should be blind to magnetization, number one. And the second thing is that rather than teaching it whether this is white or black, etc., we want to concentrate more on the critical region where we believe the complicated physics is there. And whether this learning, and there is something in critical region called universality. Universality means that even if we change the Ising model, as I've said that in Ising model, you have nearest neighbor interaction, but if we have not nearest neighbor interaction, but next to nearest neighbor interaction, then the phase diagram may look very different, but critical region apparently means where the critical temperature, etc. happens, that values change, parametric values, but critical region looks exactly the same. And that means that this plot of this critical region looks same for other kinds of models too. So this property in physics is called universality. So that's a qualitative description of what is meant by universality. Is that various things which are going through critical second order critical transition in 2 dimension, they are often governed by this Ising fixed point. The critical indices are same as that of the Ising model, although we are not getting into any kind of critical indices. These are next question. But the interesting idea is that they also visually would look very similar around this critical point. So one question we ask is that machine has to learn about this complicated nature of the phase transition and correctly identify a picture as a critical or not. Important thing is that this learning should be independent of magnetization, because magnetization is very Ising specific. So we have a method, we'll discuss what we did, and then universality. Secondly, that means that we teach our model in one spin system, but apply that model in some related but different spin system and see if the neural network can still work. And then thirdly, we need to deal with the finite size effect. We are always working with a 40 cross 40 kind of model, or sometimes 100 cross 100. Means that we do not have a sharp criticality. We only have critical region, as I have shown in these pictures, that we only have critical region here. That is this region. So what we want to correctly point out is that whether we are sampling from this region or outside. Now, what is the first thing that we want our model to be independent of magnetization? What does it mean? It does mean that we ensure this by adversarial training. So this is a concept in machine learning. What I do is that we actually give the machine some kind of bad data and tell the machine what is the bad data, so that it learns not to accept the bad data. So for example, if we take a spin configuration here, in critical region, we have said this correlation length increases, etc., etc., and you machine is supposed to find out this kind of large correlation length. Now, if we randomly shuffle this data, means the black point, white point, just mix up without changing the number of the black point, that will make this picture look more like these pictures at very high temperature. Everything is kind of homogeneously mixed up. However, these pictures and these may have same amount of magnetization. Means that if we just shuffle these things and make it look like something else, then we are not changing the magnetization, right? Because magnetization is total summation of the spin, just shuffling the spin without changing them is not going to change the total summation, magnetization. But that will destroy all kind of phase related, means phase transition related correlation, etc. Or I'm saying that this all the phase transition look like this, those things will be destroyed. So what we have done is that with our training, we are also feeding the machine this made up data. Okay, made up data is that we generate the data through Monte Carlo and we shuffle all the spins around the lattice without changing or flipping the spin and mark this data as bad. So the machine now knows that even if you have the same magnetization, machine is not blindly looking at magnetization. It is trying to learn something more non-trivial about the system, because magnetization is not something can learn. You can't just see the picture of magnetization 0.85. So this should be it can't do that because we know that, but because we are shuffling things around. So for example, generally if it is near zero, then magnetization close to that, it has a tendency to say that it's critical. At critical point, magnetization goes to zero. But as I was shuffling, even with a low magnetization, machine will immediately identify that some of those pictures are not from those kind of things. There is no long range point. It's not critical whether you have whatever the value of magnetization is. Okay, and then as I've described, we'll train our model with normalizing model, but test them in some other model. And so that we can actually check whether it has learned really about the phase transition or about some kind of specific model. Good. So what is our result? So let us go to our result. Okay, I'm sorry, I missed it. Okay. What is our result is that we will have a quick look at the result. That's the last thing I'll show you. Sorry, I missed it. Some of that part is not opening. Yeah, just give me a second.
All good?
So can you see the result? Yeah, so now I
Yes,
think.
yes, we can see it. Thank you.
Okay, good. So what the results we get is that, so here you can see a representation. So this is training on Ising model and applying on the Ising model. So no, this is the training on Ising model and applying, this is the training on Ising model and applying on, say, something related to an Ising model, not exactly the Ising model. If we do not do an adversarial training, what happens is that we can look at the proper data, train with an Ising model data and test it on some kind of related model, and we see that this green curve shows the critical region as identified by the machine, and that actually matches with the critical region of the new model. However, if we shuffle those data and feed the machine a set of junk data, still machine identifies, this is the magenta curve, although bit weakly, a critical region. Here we can see that if we go away from Ising model a lot, then the machine learning algorithm still find the critical region correctly, but again find a false critical false signal if we feed the machine some kind of wrong model, but which has same magnetization structure. So this model somehow has become more sensitive to magnetization. This is the model which has been used by people previously, not our model. What happens on the other hand, if we do an adversarial training, then this machine becomes completely immune to any kind of shuffle data. And then may shift your magnetization to whatever value, but just keeping the magnetization same, but changing other structure of the data would not fool the machine learning model anymore. So what we get now is that machine learning algorithm correctly point the rightful critical region. Actually, all kind of experiment with various values, neighboring, and these models has, and if you feed the machine some kind of junk data, which looks like Ising model data, which has the same magnetization as it has in the critical region, but there is no spin-spin correlation, then the machine immediately finds out that there is something wrong with the data. And only when we are feeding the machine, whether the new data, the test data is from the Ising model or some other model, it still finds the critical region. One important thing is that, say you take a model which is a next to nearest neighbor interaction. In this model, the critical temperature is about 4. However, our machine has learned this critical temperature has been trained by a data which has a critical temperature of 2.25. Okay. However, the machine just from the picture of those things correctly finds out the critical, what could be the critical region of the new model. Although it doesn't at all know that this is the point of this is the new critical region or anything like that. That information is not accessible. It's just dynamically find it out just by looking at the pictures. And it also cannot use the magnetization because of the adversarial training. It can't just simply think that, okay, magnetization is decreasing at some point. Okay, that should be the critical region, because magnetization is not accessible to the machine. So possibly, as we believe that I don't have time to get into all those things right now, that machine has learned about something complex about these systems. And we have repeated these experiments and kind of compared this with best possible fitting, means that something called the energy fitter, which is not a neural model, which basically is that if you can directly infer everything from energy, that's apparently could be the best thing you can do for a statistical model. And our all these classification schemes, etc., comes very close to that 99% or something very close to the exact model, etc. So this classification schemes seems to be pretty robust, and we have successfully, we believe, that trained the model for criticality. So that's what we are going to say. Many things could be done on these things, and maybe we should generalize it for other models. And there are issues like their model where there is no second order transition, but only the first order transition, or which we haven't yet done or we didn't yet get good result, is that we can just shift the magnetization of the Ising like model and still whether machine can find the criticality very well. So those are the things we are looking at. So I will end my talk here.
Yeah, thank you very much, Pallab, for the very nice talk and the connection between statistical physics and machine learning. That was really informative. Just now, question, I don't see any questions in the Q&A. If participants have questions that they want to ask in person, live, please just raise your hand and I can give you the right to speak in Zoom. Yeah. Any questions? Any hands? Okay, let's give people a few seconds to think and to formulate. Sorry, was there anything in the chat? Sorry, what did my chat just disappeared? No, I don't see questions in the chat. Okay, then Pallab, it doesn't seem that there are any urgent questions, which is probably an indication that your talk was very... here we go. Speaking of the devil. There's a question of Tutukile Kumalo in the Q&A, and Tutukile asked, which sampler do you use in the MCMC? And how do you account for the interaction of the atoms themselves, and how does that affect spins?
So in Ising model, there are no atoms. When we talked about real magnets, there are atoms. In Isaac model, it's just a spin model. We have already made this approximation that atoms could be replaced by one spin with 1 degree of freedom, this up or down. Okay. And which sampler do you use? Means this is called Metropolis algorithm. So that we just use the simplest Metropolis sampler. However, near the critical region is maybe it's a challenging thing. We often has to use what is known as block. There are some of those samplers available online. We modified those things and used it.
Thank you.
Okay.
Thank you very much. Okay. I don't see further questions now. Okay. Then Pallab, it's my pleasant duty to thank you very much for your time, for preparing a nice lecture.